I'm Luke Pulowski. I have a Bachelor's of Science in Physics and a minor in Computer Science from the University of Nebraska-Lincoln, and I'm presenting Vacuum Gravity and the Cosmological Implications. Firstly, I just want to outline the original inspiration and evolution of this model. Then I'm also going to read a short excerpt from a book that eloquently quotes my high school heroes. After the book excerpt, I'm going to discuss the fine structure of matter and the natural forces, and then move on to the cosmological model it implies. When I first read about the successful results of the Casimir force experiments in 1997, Limero, I was pretty sure I found a clue for a physicalized explanation of the natural forces, not just an exotic math trick. It was 1999 and I was a high school senior. Using excite.com, I was reading and printing everything I could find that mentioned Casimir or the Dirac sea, anything and everything, and I found Alfonso Rueda and Bernard Heisch and their papers on quantized inertia. They knew that the real implications of the quantum vacuum were huge, not just some long-range extension of the nuclear forces. It was the other way around. So, a quick primer on the Casimir force. The quantum vacuum predicted a real attraction between pairs of conducting plates. Bose-Einstein condensate, tunneling, and other things basically told us there's an empty space, energy, and it's real. Conducting plates can exclude non-harmonic waves from the gap between, while there's a full range of possible waves outside the plates. That includes the full range of harmonic waves that are between the plates, plus all other wave frequencies. The slight imbalance in total wave energy pushes the plates together, a vacuum pressure differential. Could this be analogous to resistance to acceleration and also give rise to gravity? Sure, the virtual particles cancel out, but those wave properties can transfer energy. They don't just disappear, they propagate, like light or heat, as in the book excerpt. Basically, you can't have a wave push the plates together, do work, without conserving energy. This was my first intuitive step, a real propagating effect as a result of the vacuum doing some work. Every other explanation of the Casimir force seems to discount what happens to a wave when it does work, suggesting that the particle is just virtual and gone quickly. Anyway, this is still an excellent overview of the Casimir force. The guy did his dissertation, definitely worth watching. Now for the book excerpt, also good. The never-ending days of being dead dispatches from the front line of science, chapter Why Are Loaded Fridges Difficult to Budge? Because Empty Space Impedes Them, by Marcus Chohn. According to the idea first devised in the 1960s, the quantum vacuum is absolutely central to the creation of the world. Ultimately, all bizarre quantum behavior of microscopic particles can be traced back to the relentless buffeting they receive from the ceaselessly churning quantum vacuum. Sitting in the audience of Ruda's talk, Heisch had been pretty much letting it all waft over him when something Ruda said suddenly made him sit up and pay attention. Ruda mentioned an esoteric discovery made independently by two physicists in the 1970s. Paul Davies and Bill Unruh had been exploring Stephen Hawking's remarkable idea that black holes are not completely black. According to Hawking, the immense gravity close to a black hole distorts the quantum vacuum in such a way that the fleeting virtual particles can become real, fountaining out of the vacuum as permanent Hawking radiation. Understanding exactly how Hawking radiation arises requires knowing that when virtual particles pop out of the vacuum, they pop out in pairs, typically an electron-positron pair. The positron is the antiparticle of the electron. Every subatomic particle has an associated antiparticle with opposite properties, such as electric charge. A particle and its antiparticle are always born together. Furthermore, when a particle and its antiparticle meet, they self-destruct or annihilate. Such creations and annihilations are the stuff of the quantum vacuum. All over space, electron-positron pairs are continually winking into existence, lingering in the world for the merest of instants, then undergoing mutual annihilation and winking out again. Close to a black hole, however, something else can happen. During the fleeting life of an electron-positron pair, one of the particles can find itself dragged through the black hole's event horizon, the point of no return for infalling matter. Since the particle outside the hole has no partner with which to annihilate, it has no means of popping back out of existence. It has been elevated to the status of a transitory virtual particle to a real particle with a permanent existence. All around the horizon of a black hole, virtual particles from the quantum vacuum are continually being boosted to reality in this way, flying away from the hole as Hawking radiation. Of course, ultimately, something must pay for their mass energy, and that something is the gravitational field of the black hole, which gradually weakens as it loses an equivalent amount of energy. What Davies and Unruh were interested in was exactly what the Hawking radiation would look like. They concluded that an observer looking at the black hole would see radiation exactly like that which emerges from a hot furnace. In the case of a furnace, the radiation is known as thermal radiation and has a mix of colors determined solely by the temperature of the furnace. In the case of the black hole, the mix of colors is determined by the black hole's gravity. In some weird sense, then, a black hole's gravity gives it a temperature. Black holes are hot. From this unexpected discovery, Davies and Unruh made an intriguing extrapolation. Einstein had realized that gravity is indistinguishable from constant acceleration, at least in any small enough region of space. This he called the happiest thought of my life, and made it a cornerstone of his theory of gravity. The equivalence of gravity and acceleration enabled Davies and Unruh to extend their result about Hawking radiation. Just as someone near a black hole would see heat radiation coming from the hole's vicinity, with a temperature dependent on its gravity, someone accelerating through space, that is, through the quantum vacuum, would see heat radiation coming from in front of them with a temperature dependent on their acceleration. I called this vacuum pressure differential. Anyway, I'll get to that in a bit. The virtual particles popping in and out of existence in the quantum vacuum actually have a remarkable property. If an observer flies through the vacuum at constant speed, and it doesn't matter what that speed is as long as it's constant, the view they see of the virtual particles popping in and out of existence is the same behind them as it is in front of them. This means that the quantum vacuum is completely compatible with Einstein's special theory of relativity, which recognizes that all observers traveling through space at uniform speeds see the world exactly the same way. This obviously breaks down if you're faster than light. You get a shower of Cherenkov radiation to retard your superluminal path until you reach C. Obviously true in C medium, but will hold true for C vacuum as well. Because the vacuum looks the same to an observer flying through it at constant speed, it effectively behaves as if it's not there. Just like the air in which we live, it has no discernible effect on us. However, Davies and Unruh's discovery that someone who accelerates through the quantum vacuum will find themselves bathed in heat shows that accelerated motion is fundamentally different from motion at constant speed. From the point of view of an accelerated observer, the vacuum is transformed into a real detectable thing, capable of affecting them. To Heish, listening to Ruda's talk, this prompted an intriguing thought. If an accelerated body sees heat coming at it from in front, that heat might apply a force which slows the body, says Heish. I'm an astrophysicist, you see. I'm used to the idea that heat radiation, for instance sunlight, can exert a force on bodies such as the tiny dust particles that make up the tail of a comet. So we're not talking about an ether. Below C at constant v, there's no vacuum pressure differential. All sides are filled in at the speed of light, and any anticipated Doppler effects disappear for v less than c, as all sides are counterbalanced by vacuum pressure at the speed of light. But don't forget that length contractions are physically real, and we'll get to that. After the talk, Heish and Ruda told his idea. After the talk, Heish told Ruda his idea, and Ruda said that he would do some calculations. For a few months, nothing happened. Then, one morning, Heish arrived at his office at Lockheed Martin's Solar and Astrophysics Laboratory in Palo Alto to find his answer machine light flashing. Alfonso had left a message at 3 a.m., says Heish. He was so tremendously excited by the result of a mammoth calculation he had been doing that he couldn't wait to tell me. I think I can explain Newton's second law of motion, he said. Newton's second law postulated in 1687 is conventionally written as F equals ma, where F is the force experienced by a body of mass, m, and a is the acceleration that results. The law is, in fact, no more than a definition of inertial mass, which is defined as the ratio of force applied to a body to the acceleration produced. Ruda had examined in detail the electric and magnetic components of the electromagnetic radiation experienced by a body as it accelerates through the vacuum. A magnetic field has long been known to exert a force on a moving electric charge. In fact, this is the basis of the electric motor. When an electric current, a flow of charged electrons, passes through a coil of wire placed in a magnetic field, the coil rotates on its spindle. Ruda discovered that there would be a similar force between the magnetic field experienced by an accelerating body and the moving electric charges in the atoms of the body. And when he calculated the force, he found it was exactly as required by Newton's second law, says Heish, a retarding force which depended on the body's acceleration. After 3 centuries, someone had at last explained inertia. According to Ruda, inertial mass is not intrinsic to a body at all. It is extrinsic, bestowed on a body from outside. Specifically, it arises from the interaction between the basic building blocks of matter and the great rolling firmament of virtual particles that make up the quantum vacuum. So, this is a pretty huge influence. Derivations of classical mechanics from quantum mechanics. I studied their papers and others like them. Lately, Professor Mike McCulluch has a terrific TED Talk on quantized inertia. I'll link his 30-minute presentation. He pretty much wraps up this topic with a bow while accurately deriving galactic rotation curves. He deserves a lot more than DARPA money to study reactionless propulsion. When I discussed reactionless drives with friends in college, we talked about rapid mechanical oscillations. So basically driving the Casimir plates to generate reactionless thrust by pushing on the vacuum. The problem was that the plates had to vibrate near the speed of light. In cosmological discussions about rotation curves, I suggested that the gravity carrier is itself carried by the universe as it expands. But it wasn't enough to just say that it's probably related, and I get the irony in light of what I'm saying in a minute. But some steps here, look, I get the light of what I'm, right. I'm going to make some intuitive leaps that aren't fully derived. We're coming to that. I had read about Mond in New Scientist, loved talking about it, knew it was the right track, basically. Anyway, at that time, I had to contend with objections that it's obviously not an ether as a medium, and gravity waves can't be carried along by anything. Now, I'm sure it's the speed of light that varies with the apparent expansion of the universe, a changing fine structure constant, so it can look like a propagating field effect gets a boost. So it looks like it is being carried along with an accelerating and expanding universe as it transitions to 1 over r from 1 over r squared. At any rate, watch Professor Mike McCulluch. He has this all wrapped up. Vacuum gravity. In college, I reaffirmed the idea that the force of gravity must look exactly like this model of quantized inertia, but instead of a vacuum radiation pressure differential arising with acceleration, those redshifted waves of vacuum energy were redshifted after performing the work of supporting the structure of matter. The redshift isn't lost in pair-annihilation, but instead propagates out at the speed of light and yields an exactly analogous picture to a gravity well or warped space-time. That's vacuum gravity. The primary objection to this is the implication that the sum total of the redshifts equal the total mass energy of the mass in question. But the total energy in the ambient vacuum must be pretty darn close to a singularity. Professor Baudouin's verbatim objection was, in general relativity, all energy, even vacuum energy, must have a mass associated with its energy. It would be enough mass energy to make black holes everywhere around us. Thank you, Professor Baudouin. That didn't stop my intuitive assertion, and it wasn't until many years later that I put together the significance of being inside a singularity and seeing our CMB as a real event horizon. A divergence from general relativity isn't a problem for me because I'm actually trying to derive gravity from classical wave mechanics and Maxwell's equations, with inspiration from Frank Znidarsic. I'm positively asserting mass and gravity is an effective interaction between matter and the vacuum, bestowed on a body from the outside. Chom. While I'm at it, I'm also asserting that the vacuum energy is infinitely compressible and of sufficient energy density to support observed black holes in our universe. That is to say that nearly all the vacuum energy from the direction of a black hole looks like it has been redshifted to infinity. There couldn't be a greater vacuum radiation pressure differential than near the event horizon of a black hole in our universe, or any greater massive body per unit volume, max mass. And something rather exotic happens within the event horizon. But first I have to go into more detail about the structure of matter. How does matter retard its full mass equivalence in vacuum wave redshifts? Now I reference the work of Professor Dr. Claus W. Turtur. I only know him from YouTube, because I know the model for the binding energy within matter is far more complicated than Casimir plates, where attraction and repulsion are geometry dependent, and different forces, which are less obvious than binding energy, arise from different kinds of vacuum interactions. For example, magnetic fields from vacuum polarization after supporting electron group oscillations. Basically, I have to describe something more specific than parallel plates. In college, I told people that matter could be thought of like a light pinwheel, like a Crookes radiometer, where the spin energy was just like the mass energy in matter, and that the vacuum energy kept it spinning, with the accumulated redshift giving rise to gravity. I'd asked people to think about what happens to the reflected waves. I've had this part down for a long time, and while everyone who thought that it was a neat idea usually liked it, they didn't have many ideas for experiments. not much came up in terms of experimental proposals. Thanks to Professor Turtur, I can say more precisely how the spinning happens. Quarks are relativistic coupled harmonic oscillators which pull energy out of the vacuum by following each other in a relativistically asymmetric path through an otherwise conservative field. Instead of depleting that static field which holds the repulsion or attraction to the other quarks, the vacuum energy fills in for any work done. In this case, binding the quarks or spinning the pinwheel. By filling in, I of course mean redshifting in energy proportional to the work done. For analogy, I'll take gravity because it is the classic example of a conservative field. But if you created a wormhole, and I think a slight reduction in vacuum energy density in the form of a tunnel would do the trick. To climb a gravity well, you could fall down the well over and over with a free ride up via the wormhole. You could accelerate in a loop, and it wouldn't deplete the gravitational field. The mass of the planet would stay the same, and the energy would only be conserved when accounting it via the extra redshift in vacuum energy needed to drive the perpetual acceleration of our falling body in the valve portal loop. We still have conservation of energy, but we're borrowing on a deep well of vacuum energy to power the fall, in addition to the energy that's already required to power the binding energy and forces. I use the valve portal loop because it's an easy analogy to relativistic asymmetry, which becomes significant in high energy interactions. C medium is constantly changing in response to vacuum energy dynamics or other dynamic field effects. And if you can plot a circular or oscillating path in a conservative field that's relativistically asymmetric, the vacuum will give up extra energy to support that interaction. That's the foundation of nearly all mass energy, probably all. The redshifted waves radiate out after giving up energy to support that quark bond. So to recap, the gravity well is not a fundamental aspect of gravity. It's just a useful model that looks suspiciously like a radiating body. But it's not radiating a pull, it's radiating a vacuum pressure differential, identical to acceleration, quantized acceleration, as covered above, that causes the slightly bluer vacuum pressure from the rest of the universe to push bodies together. Vacuum gravity. Anyway, let's stick to saying that the nuclear bonds are like the Casimir plates, analogous at least. The strength of the Casimir force is dependent on how close those plates are together, as well as the total ambient vacuum energy. On smaller and smaller scales, this force grows exponentially. How small are we talking? At the scale of an atom, 10 to the negative 10th meters, we have an electron in a standing wave configuration accounting for all but about 1/10,000th the cross-section of that atom, where we have the nucleus. That's a lot of empty space, nearly all of the mass energy being contained within the nucleus, and virtually nil in the electron cloud. It's with the atomic bonds between the protons and neutrons that we have fusion and fission power. The power required to bind the protons and neutrons in the nucleus is just a small fraction of the total mass energy. But it too is just a continuous process of excluding specific domains of vacuum energy and being pressed upon by the surrounding universe, kicking out redshifted vacuum waves in the process. Strong and weak nuclear force. Protons and neutrons themselves are not solid. They are made of just 3 quarks each, and those quarks are vastly smaller yet again than the protons and neutrons in the nucleus. A quark is maybe 1/100 millionth the width of the atom, and yet again their individual masses barely account for any of the mass of the atom. Matter is mostly empty space and binding energy. The bulk of the mass energy is in those bonds that hold the 3 quarks together. The entire structure of matter is more than 99% made up of different unique domains of wave cavities which are supported, contained, and buffeted by vacuum energy. The vacuum gives up energy to support both attraction and repulsion, and in the process of maintaining the structure of matter, it gives rise to an ambient, radially symmetric radiating redshift that shows an observer that same apparent vacuum pressure differential as described by quantized inertia, a gravity well. All from matter that's more of a bubble of vacuum energy exclusion zones than any physical substance. What are the cosmological implications for these energy bubbles? When a star dies, for example, the energy density of the space within the event horizon starts out pretty high and then skyrockets. Vacuum energy compression, as part of an ongoing process to sustain the gravity well of the black hole, causes a continuous buildup of energy density of the vacuum within the event horizon. This results in a dramatic energy cascade, which triggers space inflation and matter compression. The matter inside the event horizon never achieves zero volume, so no inflation, but it continuously approaches it from that moment on. This causes time to accelerate as c slows inside the event horizon, and also readjusts the size of those vacuum energy bubbles that compose matter. With an ever-increasing ambient vacuum energy density, the forces get stronger and the size of those bubbles which can be supported gets steadily smaller. Those energy bubbles are compressed. To spell it out, matter is being compressed at a steady rate in an explosion of scale that looks exactly like the Big Bang. All of the physics is playing out with an apparently constant, fine structure, but the energy density of the vacuum is going up uniformly and continuously. As the binding energy goes up, the volume required to support that exact bond strength goes down. One could also consider it as a radially symmetric length contraction. And we know those bubbles of energy are contained near C, are contracted near C, and that it's not just an optical illusion, because all the forces and structure of matter are carried by waves with the same local speed limit, c. And from the reference frame of the observer, there's no apparent contraction or time shift in any particular direction. From the inside the event horizon, this compression isn't obvious because the perspective of c staying c. Time is going faster and faster as the propagation of light is starting to slow significantly from the original c in the parent universe. The event horizon is basically fixed for the observer inside the event horizon, and yet also the universe looks like it's expanding and the expansion is accelerating. Remember, to support the structure of matter, the full mass equivalence of the black hole must be accounted for in vacuum energy redshifts, which are being accumulated at the event horizon. That energy is moving in at the speed of light from the outside universe and hitting a well, where it is forced to slow dramatically due to the previously accumulated vacuum energy waves. What propagates is the average energy of the virtual particles. The depth of that well grows very fast. After not long, it takes billions of years for light to cross the internal diameter, maybe 42 billion years, and yet the compression process continues. To what end? There's no apparent limit to the compressibility of our atoms. Since all the forces are just effects of vacuum interaction, they scale neatly with vacuum energy density. Our universe was probably formed inside a dying star. Within minutes of an event horizon forming, Within minutes of an event horizon forming, our universe had played out billions of years from our perspective. Our Big Bang and ever-accelerating, expanding universe is an implosion and ongoing compression process. As energy density goes up, light slows down and our perception of time, our experience time, goes up. Not only are space and time relative, so it is with scale. We imagine that our universe is huge and expanding, but it's staying exactly the same size and we're getting smaller. What's more, we can expect dead stars in our universe to give birth to many more baby bubble universes exactly like ours, with matter being made only of the tiniest quarks and electrons, super tiny, and the rest being standing waves and binding energy. I can't see an obvious limit to the number of successive baby bubble universes. Quite a lot, and maybe infinitely more if the scale of the quark and electron is also dependent on the available ambient vacuum energy density. Also, for sure, the total energy density of the vacuum in the multiverse is going down over time, so don't worry about that conservation of energy in a reactionless drive. It's only apparently reversed during a Big Bang due to a radical contraction of space-time. The multiverse will still end dark and cold with matter decaying, with some pockets of subjective time possibly approaching infinity. I should end this here, but this is what I'm still hung up on. I want to assume that our universe is a typical example of a universe, and that a dying star is a typical example of a black hole. I don't want to say that the number of particles is fixed due to extensive observations of our universe apparently containing a lot of particles. It could be only colossal black holes in a different kind of universe give rise to a universe like our own, but I'm more inclined to think that there was some form of excess particle genesis in a high energy environment primed by the matter which gave rise to the event horizon. Most likely, collapsed matter forms a quark condensate with more vortices than total number of quarks, because it depends on initial spin and not the number of particles. And those vortices might establish an environment where matter-antimatter asymmetry can create a universe worth of individual quarks and electrons right from the vacuum. Perhaps those vortices would prime the opposite form of matter dominance, so that each successive baby bubble universe sign flips between matter and antimatter, so our parent universe might have been antimatter dominant. I haven't worked that out in detail, but this would support the notion of our perspective being a typical perspective instead of proposing a mechanism where antimatter always loses. I don't know if this is the right type of Mexican. I don't know if this is the right type of mechanism, and I would welcome input. Thank you.